How do you describe the variation of measurement? So how do you describe variation in any quantity? So that is by its distribution. Okay, what is the distribution? So if you take a large number of readings, so practically not necessary, but to understand the process, imagine you take a large number of readings. You will get a number of readings. So each reading, how many are there? You plot a graph. What is that graph called? Histogram. Okay, histogram is the graph between number of units of each size. Okay, that graph, if you, that is numbers, if you divide by the total number, then it becomes percentages or fractions. And that, if you, is similar to a probability distribution. So measurement results are described in terms of their probability distributions. So now we are coming to statistics. So please refresh your statistics. Please see your notes, or please go through any textbook, or go through some YouTube videos on statistics, basics, what is standard deviation, what is, etc. And of course, regression is also required. So please go through your regression formulae. We'll be doing a lot of problems involving regression. So in our lab, all our calibration experiments, we use regression equations. Only we are not insisting that since it becomes too theoretical, it is not the practical oriented. But when we are used to do in the lab, actually do in the lab, so we used to determine the regression equations for all calibrations. So distribution of measurement results forms is how we describe the variation of a measurement. So the shape of the different measured quantity values. Shape of the, actually should be the frequency. Okay. So that is and if you scale it so that this is totally 1, then it becomes a probability distribution. So we compare the shape of the distribution with standard distributions in statistics. What are the distributions you know in statistics? Can you name any one distribution? You have studied many distributions in statistics, isn't it? Okay, yes, chi-square, t-distribution, normal distribution. Yes, good. So they're all distributions. So we'll be seeing, we'll be using normal distribution extensively. Normal and t we'll be using extensively. Then triangular uniform distributions we'll be seeing sometimes. So when is the normal distribution used? Whenever the measurement result is likely to be in the middle of all the readings. So it is a unimodal, only one peak is there in the histogram. So we can represent the distribution using a normal distribution. So when the measurement result is the resultant of a large number of small causes, none of which is dominant. So what is this theorem pointing to? This is a consequence of one theorem in statistics. Can anybody recall this theorem? Nobody remembers this theorem? Okay, that is the central limit theorem. Okay, so that, what does that say? So when the large number of, so when y is a sum of a number of distributions, x1, x2, x3, etc., Y will be approximately normally distributed, provided some conditions for central limit theorem are there. So none of it should be dominant. All should be approximately same size. Then all will cancel each other out. Resultant will be normal distribution. So in the book by Kirkup, they suggest a demonstration. You can do it yourself, a simulation using Excel. I don't know. I hope all of you have started learning Excel. So please learn Excel. So for the this chapter, it is easy to do the problems if you know Excel. Okay, it's not essential. You can manage with calculator also. And calculator also, learn your statistical functions. Learn the statistical functions, how to calculate standard deviation. There are 2 standard deviations. So if you use the wrong standard deviation, your answer could get wrong. Okay, so please go through the manual of your calculator and practice the functions. I mean the statistical functions, how to calculate standard deviation, how to calculate, and then how to determine the regression equation, etc. Please refresh when you come to the next class. So then we have the uniform distribution, which is uniform. There is no variation between 2 limits. So when the measurement result is equally likely at any point, you get this uniform distribution. For example, the digital output, a digital clock says 11:01. So my computer is saying 11:07. But actually it can be, I am not sure about this 15. It can be anyway. If I don't see this, the time may be anywhere between 11:07, 01 second to 11:07, 59 seconds. 00 seconds to 59 seconds. Second part, the seconds part can be anywhere between 0 to 59 seconds. So it is equally likely anywhere between these 2 limits, between 0 to 59. So we use a uniform distribution to model the digital output. Then triangular distribution is the sum or difference also of 2 dominant rectangular distributions is modeled using a triangular distribution. So if you take 2 readings using a digital stopwatch and take the difference in times, the resultant difference in time will be triangularly distributed. So the shape is triangular. Then now we come to another term, standard uncertainty. Standard measurement uncertainty. Measurement uncertainty expressed as a standard deviation. So this is defined as standard measurement uncertainty. So in VIM, everything is given with along with the word measurement. Okay. So standard deviation expressed, measurement uncertainty expressed as a standard deviation is standard uncertainty. So there is a slight difference between the definition given in the GUM and the VIM. So VIM is the latest version. So VIM definitions, normally we should follow the VIM definition. Okay. So GUM is this definition, we should treat as an explanatory definition. So this is standard uncertainty is denoted by small u. Okay. Okay. Next is combined standard uncertainty. Okay. This is a slightly difficult definition. Combined standard measurement uncertainty is the standard measurement uncertainty that is obtained using the individual standard measurement uncertainties associated with the input quantities in a measurement model. So we know that any measurement uncertainty is caused by a number of sources. So each uncertainty we model using some distribution. So the input quantities are modeled using various distributions. And there is a measurement model, that is a measurement equation. And using that, we obtain the uncertainty in the final measurement result. So that is called combined standard measurement uncertainty. You are combining the uncertainties from a number of sources. Okay, so that is the general procedure. So product of a combined standard measurement uncertainty and a factor larger than the number 1. So you multiply combined standard uncertainty by some number and you get expanded measurement uncertainty. So this is something like, so how many standard deviations will give the confidence interval, something like that. So previous definition according to Gum was quantity defining an interval about the result of a measurement that may be expected to encompass a large fraction of the distribution of values that could reasonably be attributed to the measurement. But this is actually an interval. But now actually as per the WIM, this is expanded uncertainty is not an interval. So there are some changes in the definitions. So this is evolving even now. I don't know, by next year sometimes the definition may change. So engineering, okay, we have to follow standards, then only we can communicate. So there is some difference in the definition as per VIM. So for exam, only VIM definitions will be accepted. Sorry. So expanded uncertainty denoted by capital U. So small u stands for standard uncertainty, capital U stands for expanded uncertainty. The next is coverage interval. So coverage interval is same as confidence interval. So VIM definition is interval containing the set of true quantity values of a measurement with a stated probability based on the information available. So set of true quantity values of a measurement. So this is some interval which contains all possible true quantity values with some probability. So we can have coverage interval with 90% probability or 95% probability or 99% probability, etc. And of course, when information becomes available, it may change. When more information you get to know, this may change. So that is the problem with this coverage interval. So usually we have been following 95%, practically mostly in industry we follow 95%. So some of the old books we had, so in Dublin and all, they used to follow 99%. But now, okay, it has been standardized because 99% results in a very large coverage interval. Okay, confidence interval becomes very large. So then it becomes very difficult. So just like somebody told his weight is between 70 to 100. So it is not very useful. So the way if you, most of the people will be between 70 to 100 or 60 to 100, then we can't differentiate who is heavier, etc. Okay, so it is that information becomes useless. So it has to be a small interval, then only we can do some comparisons. Okay. Okay, so now we will come to how to evaluate uncertainty. So in general, the standard permits two types of evaluations. The first is a type A evaluation. Type A evaluation is by statistical analysis of a series of observations. So you take large number of observations and do some statistical analysis, and that is a type A evaluation. Then, so what is happening here? So you have a series of observations. So that is an observed frequency distribution. So each observation, how many times you have observed, we can compute and we can get its frequency distribution. Then we fit a probability density function which best matches the observed frequency distribution. And then determine the parameters of the distribution. So that is a type A evaluation of uncertainty. So type B evaluation is by means other than statistical analysis. I think these are not the definitions. I think definitions you can see in your handout. So please take a printout of the handout and keep with you and refer it for answering questions on this. What is type A, what is type B? Okay, this is just explanation. Okay. So type A is statistical analysis. Type B by means other than statistical analysis. So any other method falls under type B. Okay. So only statistical method falls under type A. So here we assume a probability density function based on the degree of belief that an event will occur. So how will the event, what is the probability, how it is likely to change at different values of the variable. So you assume some probability density function. So either uniform or triangular, which are very popular, or normal. So uniform is among the single peak distributions, the one with the highest deviation. So that's why in most cases we assume the worst is the uniform distribution, unless it is two peaked. If you have two peaks on either side, then of course it may change. It may not be. There will be other standard deviations with other distributions with even higher standard deviation. Okay, so we have two methods in general. So many times we follow the two methods and then combine it. So do not mix up. Random and systematic components of uncertainty do not corresponding to type A and type B. Of course, you don't know what is this. So why this is mentioned is because in the UK standard earlier, before the ISO standard, they had this approach. Random component uncertainty is one component, systematic uncertainty is another component, and then you combine it. So whether type A corresponds to random, so most of the time it will be. That's the problem with this. And that's why they had to give this explanation. So most of the time, the random uncertainty will correspond to type A and systematic uncertainty will correspond to type B. But it need not be. That is what the standard says. Okay, so now we come to the actual calculations. We first go for type A evaluation, then we go for type A regression. So for next class, please come prepared, refresh your regression, how to fit a line. Please learn how to use your calculator. I don't know, last class also I told, please practice, go through the manual, especially if you are using a special calculator. Okay, learn the functions, different functions of statistics functions and how to determine the y-intercept and slope of a line. So first we'll see type A evaluation, then we go for type A regression, and then we go for type B evaluation.